Hello. Today I'm going to go over the practice forces test so you can master the actual one. First couple questions are basically warm-ups. Make sure you got the basics. Anytime I refer to an object in terms of its newtons, I'm referring to its weight or force of gravity. And as we all know, force of gravity equals m times g. And if we rearrange that, divide both sides by g, we got Fg divided by g equals m. Or in this case, 196 divided by 9.8 gives us 20. So that's how you do the first one. Second one, exactly the same idea, same formula, just we know the mass now, and we are looking for the force of gravity, because weight means force of gravity. Kilograms are mass, weight is newtons, or force of gravity. So we will just do force of gravity equals m times g, which in this case would equal 20 times 9.8, which gives us back 196 newtons. Next question, again, like, do you know your basics? Newton's second law says the net force equals m times a. And in this case, we've got a net force of 90. We've got a acceleration of 10 meters per second squared. We're looking for m. So m is equal to 90 over 10, or 9 kilograms. The next guy. So we got a couple things going on. Anytime you got anything interesting going on, draw a free body diagram for the love of all that is holy. So that's what we're going to do. Your physics teacher is represented by a box because physics teachers either do not have the inclination or time to draw something fabulous, or at least I don't. So in this case, we're going to look at the forces. Gravity down. So physics teacher is on Earth. So we got mg down. We've got normal force up. The surface just pushing straight out of itself so the physics teacher doesn't fly through the ground. We've got some forward force propelling the physics teacher forward. Maybe I'll call it applied or something, but you can call it whatever you want. I don't really care, as long as it makes sense. And backwards, slowing the physics teacher down, we've got friction. And those are our forces in this scenario. So, big trick here is this whole constant velocity. The fact that it's 30 meters per second is a big troll that I threw in there to try and get people like just plugging in all the numbers into whatever formula fits, because that's not how we do things, is it? But this constant velocity means that, hey, acceleration is how quickly the velocity is changing. If the velocity isn't changing, your acceleration must be 0. And since F net equals m times a, and in this case m times 0, your net force is 0. And net force is kind of who wins by how much. So if you have two forces fighting, it's how much the bigger force is winning by. In this case, no forces are winning. Otherwise, it would be accelerating. So we know all our forces have to cancel. So that normal force, we know that's m times g, which in this case would be 80 times 9.8. Dear, I appear to have been frozen. Hopefully this is still recording all right. So we got 80 times 9.8, which would be 800 minus 16, or 784 newtons, I believe. So our normal force equal and opposite to gravity. Also, our forward force, which is what we're looking for, this forward force here, is equal and opposite to friction. So all we have to do is find friction, and we know what the forward force is because we're moving at a constant velocity, so all forces must cancel. So we've got one main formula involving friction that is not like big minus small equals ma or forward equals backward. And that is force of friction equals mu Fn. Since the physics teacher is moving, we're going to use the coefficient of kinetic friction because that's what you use when like something is moving. If you're trying to start it moving from stopped, you'd use this one, the coefficient of static friction. So force of friction is equal to 0.4, which is our coefficient of kinetic friction, times 784, which I believe is this. And force of friction is equal to our forward force, or for applied, as we called it. So yeah, this is our answer, 313.92. Next guy, almost exactly the same, because I really want you to know this. I even underlined constant velocity here. I again try to troll you with this 26.5432, which totally doesn't matter at all, because the only thing we care about is the fact that constant velocity, so all our forces have to cancel. So we have exactly the same kind of free body diagram here. Our forward force, I'll call it forward this time, just for fun to match this guy, has to equal our friction, because otherwise it would be accelerating in the direction of whichever one's bigger. We've got a normal force up, which also has to be equal and opposite to gravity because it is not accelerating up or down, which is what it would do if one of them was bigger and you had net force in the vertical direction. So force of gravity is a mg, which is 100 times 9.8, or 980. So that means your normal force has to equal that as well. And then our forward force has to equal friction because it's constant velocity. So that's equal to friction, which is always equal to mu Fn, which in this case is 0.5 times 980, which happens to be 490. That's how it's done. In this one right here, here's kind of your situation. You've got your pony in an elevator. Scales measure normal force. Think if you jumped out of a plane with a scale, the scale would not push up on you at all and would give you a reading of 0. Or if you were being launched somehow, let's say you had a big, I don't know, comical springboard that launched you up and you're standing on a scale there, it would weigh you as heavier than normal because you feel heavier. So your sense of how heavy you are and what a scale weighs is equal to the normal force. Normal force is equal and opposite to gravity when the elevator stopped or moving at a constant velocity, and that force of gravity will not change. So Fg is 500 newtons. Pinkie Pie didn't move to another planet. She didn't go on a diet or start eating a ton of crazy stuff. Her force of gravity is still 500 newtons. But now that the elevator is accelerating, the scale is reading 250 newtons. Because remember, scales measure normal force, so your normal force is 250. So here is a free body diagram of it while it's accelerating. When it wasn't accelerating, it was just 500 and 500. So this is kind of before. Now that it is accelerating, here's our situation. So we have unequal forces fighting. One of them is winning. Gravity is winning. Since gravity is winning, since it's just a bigger number, it will accelerate in that direction. That direction is down because gravity pulls down. And our big go-to formula anytime you have forces fighting is big minus small equals ma, which in this case is force of gravity minus normal force. Force of gravity, because it's a bigger number, it's the big force. So 500 minus 250 gives us the net force. How much gravity is winning by. It's winning by 250 newtons, and that equals m times a. Remember, this formula is just basically F net equals ma. It's just we're doing the definition of net force. Who wins by how much? Gravity is winning by 250. We had to find our m in this case, but we knew what force of gravity was, and m just equals your force of gravity divided by 9.8, and so we found out it was 51 kilograms, and so when we do 250 divided by 51, we get 49 meters per second squared. And again, down because our bigger force is down. All right, next one, another tricky one. So if we do a free body diagram for a skidding rhinoceros, here is what it looks like. And this applies to anything slowing to a stop. So like a hockey puck slowing to a stop, a car braking to a stop, anything like that. Your free body diagram always looks like this. You've got normal force, you've got force of gravity, you've got friction. Now you might be like, but it's moving forward. Doesn't that mean there has to be a force? No, it doesn't. If you can't think of something pushing it forward or pulling it forward, don't put down a force. This is the situation. Now, we're also, another important thing to note is we're given a bunch of kinematic stuff. So meters per second and seconds is not something that shows up in our forces unit. So we're going to have to use the bridge. The bridge between what we've done before and the current unit is forces. So we're going to use our kinematic stuff, which we got here, to solve for acceleration. And acceleration is the bridge into forces. We can use that acceleration with our force information. So acceleration is just defined to be the change in velocity over time. It changed by 30 meters per second when it went from 30 to 0. And it took 9 seconds. And so our acceleration is 3.3 meters per second squared. Now, looking at this guy right here, we know that net force is the uncanceled force. Now, gravity is equal and opposite to normal force, so they just cancel, leaving nothing left. But force of friction has no one opposing it. So in this case, in this situation, we've got something sliding to a stop, a car braking to a stop, whatever. It's a rhinoceros sliding to a stop. Your net force is equal to your force of friction. Net force is your uncanceled force. It's who wins by how much. Friction wins by all of itself in this tug of war here. So net force equals force of friction. So net force is just m times a, and force of friction is mu Fn, in this case, Fn being equal and opposite to mg. You can cancel out those m's, and you are left with this formula here, which is true if and only if this is true. So if this is true, this is true. If this is not true, this is not true. So don't copy it on your formula sheet and start using it for all the questions, because this only works if your free body diagram looks like that, and your net force is your force of friction. Anyway, at that point, we've solved for our acceleration using kinematics. So we plug that in. We know the acceleration of gravity, and so we can just rearrange to solve for our delightful coefficient. Obviously, I use sig figs perfectly. All right, moving right along. So, only one force acts on an object. Can the object have zero acceleration? Can it have zero velocity? Explain. This one, hopefully you've gone over. This is straight out of that package I gave you with all the conceptual questions. If only one force acts on an object, it cannot have zero acceleration. You have zero acceleration if you have zero net force, which is possible if there are zero forces total, which is a very rare situation, maybe in deep space or something. You got pretty much that. But on Earth, it only happens if you've got multiple forces canceling. For every normal force, you got gravity and so on. if you only have one force, you've got no other force to cancel it. So you must have a net force, and therefore you must have an acceleration. It can have zero velocity, but just for a second. Classic example where you've got only one force is you throw an object into the air straight up. Right at the highest point, it has slowed to a stop just for an instant, but it had only one force acting on it at the time, ignoring air friction, which is fair, and that's gravity, and it had zero velocity for an instant. So yeah, it can have zero velocity for an instant. It cannot have zero acceleration. The Twilight Sparkle one, gist of that one is, like, this is a super old riddle, and the trick is the way it's phrased is supposed to make you assume that the force of Twilight on the cart is, or sorry, this is a bit messed up. So force of the cart on Twilight equals force of Twilight on the cart. So since these two forces have to be equal, like you're supposed to, like the way it's worded, you're supposed to think they're on the same object, but they totally are not. So with two free body diagrams, it makes sense. So even though this force has to equal that force, they can still end up with a net force in the same direction and the same acceleration. And we'll naturally do that. So yeah, big trick to this one is just draw two free body diagrams. These two arrows are the same length, but all the other arrows can be such that they're both accelerating in the same direction at the same rate. Just like in this case. This next guy is just like your virtual lab. Suspend a Mandalorian from a spring on the planet Hoth, where gravity is 7.5 meters per second squared. The spring has a stiffness of 1,000 newtons per meter, and it stretches 60 centimeters. So our situation, we've got a free body diagram where our upward spring force is equal and opposite to gravity. So that must mean our formula for spring force equals our formula for gravity. And remember, our formula for spring force is equal to K, which is a rating of how stiff the spring is, how hard it is to stretch or compress. So thicker, tougher springs have a bigger K. And X, how far you've stretched or compressed the spring. So in this case, we've stretched the spring 60 centimeters or 0.6 meters. These two things have to match. You want to convert units so your spring constant units match your stretch units. So we converted centimeters to meters here. 1,000 times 0.6 is 600. That's going to be equal and opposite to gravity, which is mass times 7.5. Do the math, and you've got mass of 80. Now, here is the killer one. I put this on here just because most of the rest of the questions are very studyable for. I'm not going to give you a lot of surprises, but I don't want a lot of people getting 100% who do not have mad skills. So this is the do you have incredible extra extending skills worthy of 100%. And here's how it goes. Like anything, for these questions in particular, because you will have a tricky extending question on this, you need a free body diagram. Just draw one. Make it happen. It should also be right. If you give me a right answer with a wrong free body diagram, I will not give you full marks. I am expecting a correct free body diagram for your solution. So in this case, we've got our student here who is being possessed. She's got some upward magical force shoving her into the ceiling, and she's dragged forward by a magical force of 200 newtons, accelerating in the forward direction at 2 meters per second squared. Coefficient of kinetic friction between the student and the ceiling is 0.5, and we want to figure out what is her mass. So we go and draw all our forces here. We got Mystic shoving her into the ceiling. The ceiling pushes straight out of itself like all objects do. They push straight out of their self. For your challenge question, expect unconventional normal force. So it might be down, might be to the left, might be to the right. Normal force does not have to be up all the time. That's only for flat surfaces when it's on top of them. So we have magic forward, friction back, mystic up, normal and gravity down. Now, looking at this situation, it doesn't appear that our student here is accelerating up or down, which lets us know that our up forces must be canceling with our down forces. So our 800 newtons must be equal and opposite to normal force plus gravity. So our two downward forces have to add up to equal or upward. Otherwise, she'd be like falling to the ground or crashing through the ceiling. So if we solve for Fn just by subtracting 9.8 m from both sides, we end up with 800 minus 9.8 m. Now we want to move along to solving for force of friction, so we can use it in a big minus small. Force of friction is just mu Fn, which is 0.5 times this number we came up with, and half of 800 minus 9.8 m is equal to 400 minus 4.9 m. So now we've got a expression for force of friction. And then we can just do big minus small equals ma. So we got our 200 Newton magic force forwards minus our force of friction, which is this delightful thing. And that's going to equal m times a. Notice I've swapped m and a because you're used to, in math class, seeing coefficients before your variables. So at this point, basically 200 minus 400 is negative 200. And minus 4.9 is plus 4.9. So we've got negative 200 plus 4.9 m, after minusing a minus, equals 2m. So we probably want to maybe move all our numbers to one side. So I'll kick this to the other side by adding 200 to both sides and get all our m's on the same side. So I'll move this to the other side by subtracting 2m from both sides. And I end up with this. 200 equals 2.9m. And after we do 200 divided by 2.9, we get a student with a mass of 68.97 kilograms. Just to recap, big trick here was drawing this free body diagram. We just labeled all our forces. Remember, normal force always comes straight out of the surface. And we realized, hey, our student here, our object, is not crashing through the ceiling or falling to the ground, so our up forces must have canceled with our down. And we used that to find our normal force, plugged it into our force of friction formula, which we could then plug into a big minus small. Then we just did big minus small, and even though we had m's in two different places, that's still only one variable, and the only thing we got to do is algebra to bring them together. So we got all our straight numbers together and all our m's together, and then we were able to solve for what m is equal to. Hopefully this recorded right and is useful to you. Thanks for listening.